Right now, we will have Victoria Bednar from Virginia Commonwealth University, and she will be talking to us about Terron graphs. Um, Keep in mind, if you have any questions during the talk, you can put that in the chat. And also there will be a 5-minute time allotted for questions at the end. Also, don't forget to keep your mics muted while the speaker is talking as well. So welcome, I'm super excited about your talk, Victoria.
Thank you. Again, I'm Victoria Bednar. I'm going to talk about rainbow Terron numbers, specifically rainbow Terron numbers or double stars. This is joint work with my advisor, Dr. Neil Bouchaw at Virginia Commonwealth University. So if we want to talk about rainbow Terron numbers, we have to start with Terron numbers. For the duration of this talk, I'm going to call these traditional Terron numbers, just to be extra clear when I'm talking about the rainbow version of the problem versus the original version of the problem. But generally, we just call these Terron numbers. And they kind of came out of this theorem by Terron in 1941, one of the classic results in graph theory that tells you the largest number of edges possible in an in-vertex graph, which avoids some certain clique as a subgraph. The formal definition is here, but basically just consider you have in vertices, you want to avoid some clique. What's the most number of edges you can put between those in vertices to avoid that clique? One of the remarkable things about Terron's theorem, which we don't see often in extremal graph theory, is not only does it tell you the exact extremal number, the exact largest number of edges you can have, where typically we have an upper bound and a lower bound, or maybe just a lower bound, or maybe just an upper bound. This gives you the exact number of edges, but it also tells you exactly what the graph has to be. It gives the unique extremal graph, which realizes this number of edges, which is another thing that we don't see often in extremal graph theory. As a result of Terron's theorem, extremal graph theory took off, and we get formally defined the Terron number of a graph, which is a generalization of this concept, as the largest number of edges in an in-vertex graph, which is H-free. And we denote that number EX in H for the extremal number on in-vertices, which avoids an H subgraph. A rainbow edge coloring is an edge coloring in which every single edge has a unique color. So when we're looking for rainbow H subgraphs, we're going to properly edge color all of G and then look inside of G to see if we can find any H's within that proper edge coloring of G where every edge of that H has a unique color. Then the rainbow Terron number, EXR in H, and it's sometimes denoted EX star in H, is the largest number of edges in an in-vertex graph, which is rainbow H-free, or some proper edge coloring of G. The word some here is very important because you could have every single proper edge coloring of G, which has a rainbow H subgraph, except one. And as long as you have one proper edge coloring of G without that rainbow H, then it satisfies this. There's two kind of things working underneath this definition. The first is what I just said, that as long as you have a single proper edge coloring, avoiding a rainbow H, this is satisfied. The second half of that is for every single edge that's not in G that you add to G, every proper edge coloring of that new graph must have a rainbow H. So the second statement here is saying a lot. Every missing edge, once you add it, every possible proper edge coloring has to have that rainbow H subgraph. And it's worth noting that these proper edge colorings of your new graph G plus E are not necessarily related to the proper edge colorings of G without E added. You're considering G plus E as a completely new graph, and you might be able to create proper edge colorings out of what you had for G. But again, you have to consider all of the proper edge colorings individually. Well, not technically individually, but you have to consider all of the possible proper edge colorings, which means that just extending what you get from G isn't good enough. The rainbow Terron number was formally defined in 2007 in this paper by Kivash, Mubayi, Sudakov, and Verstrada, aptly named Rainbow Terron Numbers. Super interesting paper, highly recommend it. And two of the results, which we'll see more as we go on, is this general upper and lower bound they give for the rainbow Terron number. For us, it's important to see that the rainbow Terron number is bounded below by the traditional Terron number. If you consider this, if you would like to avoid some rainbow H subgraph, but you just forbid all H subgraphs, well, you're never going to have a rainbow H because you're never going to have an H. So we can almost trivially bound it below by the traditional Terron number for H. The second result we get from this paper that we'll use further is the reduction method, which gives us a way to bound the rainbow Terron number above by a traditional Terron number. For this, we take our graph that we're trying to avoid. Consider we want to avoid a rainbow P3. Well, we can color a regular P3 like this, properly edge color it. However, just by adding one extra edge, this new edge has to have a new color. And so there's a rainbow P3 embedded in this larger structure. So by forbidding this larger structure, we are forbidding rainbow P3. We're also forbidding that extra edge. So the traditional Terron number of this larger structure gives us an upper bound on the rainbow Terron number of P3. And that's the reduction method in a nutshell. So highlighted in green, we have an upper and a lower bound for the rainbow Terron number, both based on traditional Terron numbers, which are much more well-studied, much more well understood. We have a lot more tools and machinery to consider them. So it's an excellent way to go as opposed to what we're going to see here. This is partially a reiteration of what I said a couple of slides ago. When we want to find an upper bound, we have to show that every graph with our upper bound number of edges and every proper edge coloring of all of those graphs all contain our rainbow forbidden subgraph. So that's a lot to prove. Or we can use the reduction method, try to augment our graph and use a traditional Terron number and get an upper bound that way. For lower bounds, we have the traditional Terron number, or we can construct a graph and just show that there is one proper edge coloring of that graph, which doesn't have the rainbow forbidden subgraph. So that's a lot less, right? For the lower bound, we have one graph and one proper edge coloring, whereas for the upper bound, we have every graph and every proper edge coloring. We need one more tool before we get to double stars, and that is the Aeroshock Conjecture, which we will use in conjunction with the reduction method. Aeroshock Conjecture is from 1963. The idea behind it, it gives the extremal number for all trees. The idea behind it is that a star is kind of the densest tree you can have. A path is kind of the least dense tree you can have. They both have the same Terron number, same traditional Terron number. So all of the trees in between should have the same traditional Terron number. There was a proof announced a few years back that hasn't been published, but many specific cases of the Aeroshock Conjecture have been proven and published. In particular, we'll use this one from McLennan, 2005, which says if the diameter of our tree is at most 4, then the Aeroshock Conjecture holds. All of the graphs we'll look at have diameter 3, so we're good to go. All right, now we have everything we need to start talking about double stars. A double star is 2 stars with an edge in between. We call them DS, RS for the number of leaves, R leaves and S leaves, and further specify that R has to be less than or equal to S. This is important not for the definition of a double star, but because of our bounds, where we double R in this upper bound, if we use S, which is larger than R, and double that one instead, we'll obviously get a worse bound. So we just specify R is less than S, less than or equal to S, so we can get the best bound possible with this method. The upper bound uses the reduction method and the Aeroshock conjecture. So if we consider this, and we want to color the tree above, oh, I had my eraser on, there we go. If we want to consider the tree above with R and S leaves, we can color these, number one, these edges adjacent to these leaves, colors 1 through R. We can repeat colors 1 through R here because they're not adjacent to the leaves on the other side. And then we would have S minus R new colors. However, if we add in R more leaves here, augment that graph the way we were talking about for the reduction method, all of these leaves have to have new colors. And so we'll have that DSRS rainbow inside of this DSRS plus R. I didn't bother giving this backbone edge a color, but obviously that one would have a color as well. It just doesn't go into that calculation of how many leaves you have. So we use this new tree, this new double star with the Aeroshock conjecture to get this upper bound. The lower bound comes from an observation using Ising's theorem. If we would like to rainbow color this, rainbow edge color a double star, then we need the same number of colors as the double star has edges, which is R plus 1 colors. However, if we know we can color a graph with only R plus S colors, then we know we can color the graph without a rainbow DSRS because we can color it without enough colors to get there in the first place. Ising's theorem tells us that the edge chromatic number of a graph is either delta or delta plus 1. And so we use those two things together to get this lower bound. Here's a special case of double stars where we do actually know the exact rainbow Terron number for them. These are double stars with 1 leaf on one side and an odd number of leaves on the other. The lower bound comes from construction. So we have our K to K plus 4. So it's an even complete graph. So we know that it has the canonical edge coloring, which is every color is used the same number of times and every vertex sees every color exactly once, which tells us up to isomorphism and exact edge coloring that we can give to all of these even complete graphs. And the canonical edge coloring will always avoid these odd brooms or these special double stars. The upper bound is just a particular case of the reduction method using Aeroshock. You get the same number for both of these, which is this 2K3 plus 3N over 2. The little o of 1 just takes care of any divisibility issues that may arise. But the main important part here is this 2K plus 3N over 2 is the rainbow Terron number for this special family of double stars. I think I'm just about out of time. So I'll just come here and talk about what's next. Improving the lower bounds for the rainbow Terron numbers of double stars. All we have so far is the observation using Ising's theorem, which you don't get as much mileage out of as you'd want to, and the traditional Terron number, and in some cases construction, but finding tools to get better lower bounds for these rainbow Terron numbers of double stars. We didn't have time to get into K-unique Terron numbers, but they're in between traditional and rainbow, where you can say, I want 5 unique colors, or I want 3 unique colors instead of all, or I don't care. And then brooms and caterpillars are the natural extensions of the concept of double stars. That last double star we saw, which had one leaf and an odd number of leaves, is a kind of broom, but a broom can have as many backbone edges as you want. And then a caterpillar, so if this is our broom, then a caterpillar can have as many leaves at each vertex along the backbone that you want. So these are natural extensions of that concept of a double star. And then maybe way in the future, looking at rainbow saturations for problems for double stars. And that is about all I have for you guys. I think I'm just about out of time.
Thank you very much for that awesome talk. If you don't mind, go ahead and unmute yourselves and let's give a round of applause. Does anybody have any questions?
Yeah, I would like to ask a question. I'm wondering, are the rainbow Tura numbers exactly known for the, say, for cliques?
No, I think there are no rainbow Terron numbers exactly known, except for like the star and a triangle, because those are rainbow graphs. It doesn't matter, right? The proper edge coloring of a triangle is always rainbow, and the proper edge coloring of a star is always rainbow. So those are the same as the traditional Terron number. But there are honestly not a ton of papers out on rainbow Terron numbers, even though there are a lot of people working on them. They're fairly new, and we don't have a lot of machinery for looking at them.
Thank you. I have one more question. You showed this result by Kivash, Mubai, Sudakov, and Bastrat about that the rainbow Tura number is essentially the Tura number up to that small law of n squared error term. And here I was wondering, is there a similar result for hypergraph?
I'm not exactly sure. I know that I don't think that there's anything that like specific about hypergraphs. There is like some brief discussion of hypergraphs in that same paper, but the results are kind of a different flavor than for the regular graphs.
Yeah, it's probably much more difficult anyways.
I think they basically, if I recall correctly, they basically define what the problem would look like for a hypergraph and give some ideas of like how you might look at it, but there's not a lot more than that.
Okay.
Are there any other questions?
I'd also like to ask about that upper bound of little o n squared. As somebody who's outside the field, like that strikes me as like not as strong as it could be. And is that just wrong? Like, is there anything known about like how what that function might look like?
The short answer is no. The proof for that upper bound is very complicated. I think it takes up multiple pages just to get that little o of n squared. So it does give you, it's a kind of the same idea as just using the traditional Terron number for the lower bound. It gives you a bound, but depending on what graph you're trying to avoid, it's not probably a good one.
Okay, thank you. If there are no other questions, I have another one. Why you say your next step, your first thing on this list is to improve the bounds that you have? Is it easy to say like why you believe that like you should be able to push in that direction?
Yeah, so for the double stars that we have so far, or the bounds that we have so far, the reduction method is we don't have to add many more edges for the double stars. And so intuitively, I think that that should be a closer bound than just this, oh, well, you can color the graph with not enough colors, which doesn't have anything to do with the actual structure of the graph or anything like that. And so my idea is that like we should have developing better tools for the lower bounds would get the lower bounds closer to the higher bounds and not vice versa.
Thank you.
All right, so let's go ahead and thank our speaker again.